Welcome back everyone. Today we learn about energy. The areas we will be focusing on are exothermic and endothermic reactions, heat exchanges, bond breaking and formation, and energy calculations. Looking at the diagram on the left, the energy level at A is higher than that of B, and at a higher energy level, A is less stable and thus is more chemically reactive. Enthalpy is synonymous with energy level, and when the enthalpy decreases from A to B as seen in the diagram, the products are more stable than the reactants. And hence the enthalpy change is less than zero. And when heat energy is given off, it is an exothermic reaction. On the other hand, when the enthalpy increases from B to A, the products are less stable than the reactants, and hence enthalpy is more than zero, hence since heat energy is taken in, it is an endothermic reaction. Therefore, when A becomes B, since heat energy is given out, the temperature increases. On the other hand, when B becomes A, when heat energy is taken in, the temperature decreases. Bond formation requires energy to be given out, and hence it is an exothermic reaction, while bond breaking requires energy to be taken in and hence it is an endothermic reaction. An example is the combustion of magnesium and oxygen. This reaction is exothermic as seen in the diagram, and since heat energy is given out, temperature increases and bonds are formed. The meaning of enthalpy change is the heat change when the reaction takes place between number of moles of reactants as determined by a stoichiometric equation for the chemical reactions, and its unit is kilojoules per mole or kilojoule. The factors affecting enthalpy change is temperature, physical states of reactants and products, pressure of gaseous reactants in products, concentration of solutions, and lastly the number of moles. Here is an example of an energy calculation of the reaction between hydrogen and oxygen to form water. The enthalpy change is minus 484 kilojoules, and it is the formation of 2 moles of water and also the combustion of 2 moles of hydrogen in excess oxygen. Since it is a negative value, the reaction is exothermic. The enthalpy change of neutralisation for the reaction between strong acids with strong alkali is the same and at around 57.3 kilojoules per mole. The reason for this is because most of the strong acids and alkalis dissociate completely, forming ionist H+ and OH- ions. The enthalpy change of neutralisation for the reaction between weaker acids with weaker alkali is less than negative 57.3 kilojoules per mole. The reason for this is because weaker acids and alkalis are partially dissociated to form ionist H+ and OH- ions, and thus less energy is released as part of the enthalpy change. Examples. Some examples of exothermic reactions are nuclear fission, combustion, respiration, and neutralization. Some examples of endothermic reactions are photography, photosynthesis, and decomposition of compounds. Calculation. Bond energy can be negative, and a negative value indicates the energy released after the bond is formed. Bond energy can also be positive, and a positive value indicates that energy is absorbed after the bond is broken. An example of calculation of enthalpy change is the reaction between hydrogen and iodine to form hydrogen iodide. The way to calculate this is to add the energy required from bond formation to the energy required for bond breaking. In the case of the reaction above, the enthalpy change is negative 11 kilojoules per mole, and it represents 1 mole of hydrogen burns and 1 mole of iodine to form 2 moles of hydrogen iodide, and 11 kilojoules of heat energy is being released. In order to produce 20 moles of hydrogen iodide, 10 moles of hydrogen is needed, and thus an energy change of negative 110 kilojoules would take place. The second example is that of carbon with oxygen to form carbon dioxide, and similarly to calculate the enthalpy change, we need to add the energy from bond formation to the energy required for bond breaking. The enthalpy change of the reaction is negative 990 kilojoules per mole, and this represents 990 kilojoules of heat energy being released when 1 mole of carbon burns in 1 mole of oxygen to form 1 mole of carbon dioxide. In order to burn 10 moles of carbon, 9,990 kilojoules of heat energy is evolved. Let's look at another example and determine whether the above equation is exothermic or endothermic, given the bond energy stated below. On the left-hand side, one HH bond is broken and one Cl-Cl bond is broken. On the right-hand side, one HCl bond is formed, and therefore applying the formula for enthalpy change, negative 184 kilojoules of energy is released, and thus is an exothermic reaction. Energy profile diagram. This diagram is called the reaction pathway or energy profile diagram, and do note that the earlier diagram drawn is an energy level diagram, different from the one shown here. Does this diagram indicate that A to B reaction is easy to occur without any energy input required? The answer is no. These diagrams do not show whether such chemical reactions is feasible and can occur. Activation energy seen in the diagram is the factor governing the occurrence of a chemical reaction. Enthalpy merely shows the stability and whether the reaction is exothermic or endothermic. Enthalpy is independent of activation energy and vice versa. In this diagram, the enthalpy change is less than 0, and thus is exothermic. On the other hand, in this diagram, the enthalpy change is more than 0, and is thus endothermic, and usually for endothermic reactions, the activation energy is larger than that of exothermic reactions. That's all for today. Thank you for the effort to learn with me. Stay tuned for more interesting lessons. See you next time. Bye-bye.